And same deal as multiple choice, same set of rules. And the 20-minute, it's the same deal. It's the anti-check measure. When I thought, oh yeah, 20 minutes, that's so short that you can post a question on check and get a response back. And although it wouldn't work as an anti-ChatGPT measure, keeping it for now. One, I don't know if ChatGPT can be relied on to produce correct diagrams at this point. Like I can imagine someone attempting to use, again, a cheater, attempting to use ChatGPT for freeform timed assessment, and their answers probably will be noticeable in that it lacks diagrams. Because diagram is really the weak point of large language models at the moment. It can do some diagrams, but it's getting better. So let me start now. A full disclosure, I have actually looked at the question before. It's because I've already done a few of these freeform timed assessment for electrostatics demos. Like there are 3-4 questions that's already been done. So I want you to make sure when I hit start here, it wouldn't land on one of the questions I've already done. So I opened it, looked at what the question test student will get, and I made sure that it's not the exact same question I've done. It's similar to one of the questions, but it's different enough that it'll count as a different question. So, but I promise I haven't had a lot of time to think about the question. So this is a genuine attempt within 20-minute kind of demo. I do know enough that it's about electric potential. Again, I looked at the question before. But I didn't read it other than to ensure that the other demo I've already done, it's electric fields. So, okay. Calculate the electric potential voltage for the situations below. Whenever possible, good. That's what I was going to do anyway. Consider the dipole arrangement. The dipole arrangement of charges separated by distance d. And so on. Yeah, this is just defining what's in the figure. Calculate the electric potential in the space around the chart as a function of coordinate. X and Y. Oh, it's a general expression. So what I need to do is, so this is my thought process. I'm going to use the fact that I know the electric potential of a point charge. It's given as a Coulomb constant times the amount of charge divided by R. Scalar. It's not a vector. Potential is so much easier to work with. Now, so based on this, I might say that the voltage due to the positive charge is KEQ plus divided by R. Oops, not Q plus, sorry. Q, or I guess I could say plus Q divided by R. And V minus is KE minus Q over R. And say the total voltage is V plus V minus, and say it's 0. That would be a mistake. The main mistake is in how you handle R. So I guess the easiest way to do it is this R, it's meant to be R from the positive charge, R from the plus Q, and R from the negative charge, R from minus Q. So it takes a bit of consideration to come up with a correct expression for that R. So let me draw kind of the picture to kind of help me think through this. So if I have those two charges, my coordinate axis defined this way with the X and Y. These distances are d over 2. Then I'm gonna just pick a kind of representative point at somewhere and random point in space, like over here. This is my representative point. What is the R plus, and what is R minus? That's the question I need to answer for myself. So coordinate of that point would be coordinates, let's say X and Y, and I guess I don't have to deal with the G. So X and Y. So Y coordinate, I think I can use it as it is, because perpendicular to the displacement. It's the X coordinate that I have to be careful. The X coordinate. So for calculating vector or figuring out vector R plus, what I have to say is that for that point at XY, the Y coordinate is fine. I can just leave it as Y. For the X coordinate, I have to account for that it's to the right by some distance, not to the left as shown here. And I think I think through some potential guesses, and the guess I have is x plus d over 2. That way, if you have negative x positions up to d over 2, it'll be still positive, and then at d over 2 it'll be 0. And then if it's even more negative, it'll now be negative, but you'll subtract d over 2. And if you are in the positive direction, then you're simply adding d over 2. So I need to have an expression for this based on that. And I think through r minus also, and if you do, that this should look like something like this. The y coordinate, I can still keep it, but the x coordinate now should be, I think, x minus d over 2. That makes this particular one, is that right? Yeah. So x is negative here, and I think let me erase this x, that's confusing. The x for that point is negative here, and then I'm subtracting minus d over 2, making it even more negative. And so as you have positive x up to d over 2, this is going to be a negative quantity, and at d over 2 it's a 0, and then so on. You can also do it by writing this in Cartesian coordinate system and then do a translation operation. That's another way to do it. Either way, you figure out the correct expressions for those displacement vectors, and then the magnitude it's easy. This is a square root of the r plus dot to itself. I think it's easy enough. I can just write it out as I go. So it's of course not 0. So for the total voltage, I need to have V plus. So I guess let me write out this much. I can factor out some common vectors. I can factor out K, E, Q, and then the uncommon factors will be 1 over R plus minus, from the minus sign, 1 over R minus. And I'll write out what these are as I type it here. In the interest of time, I think I might already be running out of time. Yeah, I already used 5 minutes. So let me do, so KE times, by the way, this will also accept as correct versions based on permittivity of free space, just because. 1 over, I need the square root of, so that thing squared, x plus d over 2 squared plus y squared minus 1 over square root of x minus d over 2 squared plus y squared. And you can do kind of sanity checks. Basically all the points where x is equal to 0, this should add up to 0, like the midway point, that's the 0 volt equipotential. And if x is 0, then these denominators are the same on both, so when you subtract you get 0. So but that should be correct. Let me move on to part B. I think they are not all that related. Total torque Q naught is uniformly spread over thin insulating rod of length L as shown below. Find the electric potential at the location of point P at distance B from the nearest. So here, I don't think this question is all that much simpler than the electric field version. You just have to integrate. You do use the fact that the voltage of the point charge from Coulomb's law and doing the integral using universal reference. So that is K, let me call this lowercase q over the distance. I guess I can call it r. It won't be confusing with anything else. So it helps to kind of set up the integrand for a representative point. So you can't use the formula for the point directly for the entire rod because it's spread out. Not all charges are at the same distance. So I'm gonna consider one kind of representative charge element spread over interval dx that has amount of charge dq. And let me set my origin so that my x is equal to 0 here, and so this is at the value x, and this is where x is equal to L, and x I'm only going to use it to integrate over the rod, so I don't really need to specify x outside of that. This is just distance b at point P. So I consider what I call infinitesimal voltage contribution from this infinitesimal charge element. I can treat it like a point charge, so it's going to be constant K times infinitesimal amount of charge dq divided by the distance. So I look at the geometry and figure out, this must be b plus this bit, which is L minus x. So divided by b plus L minus x. Okay, so that's my kind of, so thinking through this, I think this is the part that a lot of students struggle. Once you have this much, then next few steps get easier. In order to get the voltage due to the entire rod, what you need to do is integrate these infinitesimal contributions over the entire rod. And what that means is, well, I'll just say rod. I need to kind of expand out what this dq means, because integrating over that dq kind of doesn't make sense until you express this basically as a function of x. Then you can integrate with respect to x, get an answer. So I need to think through, okay, dq in terms of x, what does it look like? I think it's gonna be dq will be proportional to dx. And I think through, well, what's the constant of proportionality? Well, I guess I can write this. This is the kind of the fraction amount of charge over q naught, and dx, kind of extent of that piece over the entire rod. And does it say, yeah, uniformly? So that's what justifies this equality. So from this kind of proportionality relationship, I can say dq is q naught over L dx. You can also think of this like the linear charge density lambda over x, which happens to be constant here. So with that substitution, what I have is Ke q naught over L dx finally, divided by b plus L minus x. Now I can be more specific about what integrating over the rod means. It means I am going from x equal to 0 to x equals L. And setting these limits is where you have to be careful. Sometimes it's easy to make a sign error as you are setting the limits. And what I do say is it helps, it's best if you kind of have a sense of if you expect a positive answer or a negative answer, and if you made a sign error, just fix it at the end. Like there are some situations where I'm not sure if I'm making sign error or not. But if you have, so here I have a good intuition that if a Q naught is positive, potential here should be positive. So if I get a negative potential, I'll just fix that sign error. So for this integral, it looks like I'm going to be doing u substitution. So let me factor out all the constant coefficients that I don't need to bother with. Ke q naught over L. So I have dx over all this. I'm going to use the u substitution with the u equal to b plus L minus x. Then du is equal to minus dx. I'm going to be substituting these in, or imagine having solved it for dx and x and substitute it in. And I'm also going to change the limits to match the limits in terms of u. So with the substitution, so this dx becomes minus du. Let's hope that goes away somehow. And the entire way I chose this u was so that this denominator would be u. That way I can integrate easily. The limits, if I plug in x equals 0, then it becomes u equals b plus L, and plug in x equals L, and it becomes u equals b. I'm hoping this kind of reversed limits will cancel out the minus sign. This is a pretty easy integral. Hopefully everyone knows how to do it. The antiderivative of 1 over x dx is natural log of x. So that's what I'm going to use. I'll say minus, pulling out the minus sign, Ke q naught over L times the antiderivative, natural log of u, evaluated from limits b plus L to L, so not L, b. So plug in these limits. Let me just do it in place in the interest of time. Plug in these limits. This becomes natural log of b minus natural log of b plus L. And I can do a little bit of logarithm algebra. This subtraction that makes it so that, combine the natural log, it's b over b plus L. I think both versions would be graded as correct, but this is the kind of the simplest form. So v at point B, and with the minus sign there, and b over b plus L being less than 1, so I can do this. I can absorb that minus sign into here using logarithm algebra. Then it becomes equals ke q naught over L times natural log of b plus L over b. This is manifestly positive because that's a ratio that's bigger than 1. Natural log of that will be positive. So that's the simplest form. Ke times q naught divided by L times natural log of my open method does implicit multiplication, so I don't need to put a multiply by sign if I don't want to. So that should be correct. How much time? 5 minutes. I'm running out of time. Consider uniformly charged sphere, to outside. Okay. Show the derivation of any formulas you use. Okay, I'll do it later. I know it's gonna be and show the derivation of any formulas. This one is actually a bit complicated. Maybe 5 minutes is enough. So B, C, I will say do it later. And you are allowed to do that. You are allowed to work on your work after you've done it. So I guess there's a kind of judicious call to make. So inside it's a uniform sphere, right? Uniformly charged sphere, yeah. So I don't know how much detail I have. Well, there's a kind of range of different amount of details you can put. So with the charge density rho, where rho is equal to q over 4/3 pi r cubed, I think I can remember the electric field formula. So electric field outside is Ke q over r. Electric field inside, I know it's proportional to r from having derived it with the Gauss's law before. So the way I would do it is I'm just gonna guess at some formulas. It should be Ke q over r squared times r. Yeah. So I do think electric field would be continuous across the boundary. That's how I'm guessing. When small r is equal to the capital R, so right on the radius of the sphere, the formula from outside should match the formula from inside. So I'm pretty sure this is the correct formula when you go through Gauss's law and all that. So now what I need to do is I need to figure out the change in voltage from surface to R. So that's going to be minus of the integral from R equals capital R to the R equals R. Sorry, I'm abusing notations. Don't report me. I'm going to be using this form, R dr. So the antiderivative, let me pull out all the constant factors. Antiderivative is r squared, and I'm evaluating it from lowercase r to the lower limit capital R to the upper limit lowercase r. Don't report me. If I'm doing this properly, I would put like primes here so that so that I'm not I'm not arrested by math police. Okay, 2 minutes. So with that, so I have minus K q over r squared minus capital R squared. Did I make a mistake? Oh, I didn't make a mistake. This is supposed to be squared, which means this is supposed to be third, third, third. So yeah, with the correction, it's fine. So inside the sphere, it should look like this. Let me just make sure I have more than a minute. A minute, I think. KQ over. I guess I'll do it this way. Alright, this is the from like a voltage at the surface, and now I'm typing the difference. Minus KQ over R to the third power, and then R squared minus R2 squared. I think that's right. Unless the units work out, and let's make sure as you go in you get more positive voltage, I think. Yeah, when R equals 0, that's when it's most positive. I think that's right. Hopefully. So I'll add a little bit of addendum. For C, I used the memorized formula for voltage of point charge. Didn't think I had to derive that, and you can argue. One could argue that such a basic formula that one would have it memorized. You don't need to derive it. For the I could do the full Gauss's law application for E field formula, and this is something we might do in the one-on-one meeting. E field formula inside the sphere, but I was running out of time. I probably could have typed this out of time, so I made a guess using continuity of E when there's no surface charge. Let me paste all this work. And now some of these timed assessments are set up in a way where it auto-grades. All these boxes, they actually auto-grade the expressions that you put in. So we can see if I got all the parts right. And if I missed anything, I'll go to the solution and make sure you have the correct answers. I won't leave you with the incorrect answers that I might have inadvertently made. So let me paste this in. How far do I go? I think maybe here. And zoom out a little bit so I can just do the whole thing in one screenshot. All right. Save work and code. Now it won't be 100%. It's because of this box that graded as incorrect or 0 point. So it's got 1, 2, 3, 4, 5 answer boxes. So if I got all the parts right, I should get 80%. And I got 40%. What did I miss? Um, 40%. So that means I got 2 parts right. Let's check. Didn't think I made any actual serious mistakes. I'm gonna go to the attempt in my second screen. I'm going to the test student's attempt, and well, I'll have access to answer key. I can show you what that looks like. I mean, I can show you what the answer key looks like. So here's the test student's attempt. Yeah, grade is correct and is correct, and it accepts the other version as well. This is incorrect. This is incorrect. P nearest. K Q naught over L. Oh, I made a typo. When I was writing it out here, I wrote it correctly here. But when I was typing it, I must have been looking at this, and my brain mixed up the expressions. So it's graded as incorrect, but I contend I didn't make actual mistake. It's just typo. And wait, this one wasn't correct. I thought this would be correct. K Q over R plus. There's a factor of 2 I miss. Oh, yeah, I did this mistake I did make. In doing the antiderivative, I missed a factor of 1/2. So yeah, okay, yeah, that is an actual mistake. I shouldn't have done it. This is what happens when you are in a hurry. There's a factor of 1/2 in the antiderivative that I forgot. So yeah, mea culpa. That's the correct. Now there's a detailed solution that you can read. It's not just the answer there. There's also a detailed solution that's available. I think this comes from earlier time when I was coding in freeform timed assessments when I wanted it auto-graded. Most of my freeform timed assessments are not auto-graded, but this class has some of the questions that are coded that way. I started doing it that way after a while.